The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
Okay, hello, I'm Tyler. We're going to talk about Rust Interop. This is not going to be nearly as controversial as you might think it would be. It's I'll just tell you the punchline up front. It's easier than you think. There's a thing I love about C++. I feel like C++ is the greatest nerd snipe. It has so many dark corners you can stare into, and sometimes there are buses full of money that keep running into us and keeping us coming back to it. And there's this other language that I think has a lot in common. I got started with it about 3 years ago, and it's been great. To continue, C++ is full of fiddly little details. I remember this, Timur posted this on Twitter after the CPP Stories guy wrote a book on initialization, and there's a lot of little details. And this is the feeling that I get doing Rust Interop. There's a lot of little details, but none of them are really that hard by themselves. It's just the culmination of it feels challenging, but if you break it apart, it's not that bad. In the past, I felt like this was a vibe I would get in the C++ community. That seems to be changing. I think it's, I think at first, new things feel threatening, but they can be full of wonderful things that we can learn, just different ways of thinking about things. So let's get started. In the beginning, what we're going to do is just glue these two things together. We're going to ignore the rest of the details. We'll come to them later, and we're going to do it in the simplest way possible. What I mean by that is we're going to do it in the most manual way possible, because we are still fairly early in Rust and C++ interop, and so even if you use code generators, even if you use a bunch of tools, you still end up in situations where you have to do it manually. You have to pull it apart and see what's happening. Sometimes you have to add things yourself. This all comes from stuff that I've done. I was in this situation where there was a large C++ library that I worked on, a bunch of applications built on top of it, and various robotics algorithms were implemented in plugins so that you could compare the plugins and so that you could, at runtime, swap out things. I had written some new robotics algorithm code in Rust, and I wanted it to include it with this rest of this application. So that's where I got started with this. The basics of Rust Interop is you're building a bridge from two places that are comfortable and easy. There's safe Rust. We're not going to talk much about safe Rust in this talk. There's plenty of resources on how to learn to write it. And on the other side, we got our C++ header file. We're going to present a well-behaved C++ thing that our users, so our users don't have to look underneath. The content of this talk is largely about the middle there. We're going to build some unsafe Rust with a C interface, and we're going to write the implementation for that header in a source file that uses that. You'll see there are some logos here, or some characters. One you may not be familiar with is Koro, the unsafe urchin. It's a fun character, and I like it a lot. Everybody knows about Ferris, but we got Koro also. It's a different language in some ways. So this is where we're going to start. We have a joint type. The real one had a lot more members to it, but this gives you a good flavor of it. And we have a function that will create a new one. And on the Rust or on the C++ side, we want a joint type that contains this Rust type. So we're going to make a move-only type. You may see I don't have a copy or move construct or copy or constructor or assignment because I've specified a move assignment or defaulted one. The compiler will helpfully delete it for me. Also, you're going to see a member variable that will also have that effect. The only thing I have to specify is the constructor. Everything else is default in this case. On the unsafe side, on Coro's side, we're going to write a couple C functions. One to create a new object and one to delete it. This is a matching pair. And the reason we need this, among many reasons, is your allocators and deallocators have to come in pairs. If you allocate something in Rust, you need to deallocate it in Rust. Because the memory layout is different. And you can get in a lot of surprising trouble if you try to mix a deallocator on C++ side. So we have this function that'll call the new, and we have one that'll call the delete, essentially. And you'll notice the new, there's no unsafe in the new. There's a couple details here. There's no unsafe in the new because it is safe to create and leak memory. There's nothing UB about doing that. There's a couple other details. There's this no mangle attribute. That's because Rust, like C++, mangles function names. And we need it to not mangle this function name so that we can link to it and call it through the C interface. And then there's extern C, which tells the compiler this has C calling conventions. It'll make sure that I only put types in it that can be called from C or represented in C. The deleter, it is unsafe. We're taking in a raw pointer, and we're going to get this at link time. So the compiler can't see through to the call site. So it can't know anything about the lifetime of this raw pointer. It can't know that it's valid. We're going to write the other side. A lot of what writing good unsafe code is about is carefully checking and then building a well-behaved interface for your users. So you write it in pairs. You write the call site and the consumer. On the C++ side, in our header file, we have a unique pointer that's going to store this opaque pointer to the Rust object. We need this because later we're going to make methods on the Rust side that we're also going to have a pair of on the C++ side, so we need the object to be able to call it. The deleter, you remember robot joint free was that function that I wrote. We have a template here that's part of the unique pointers template arguments that I will show in just a bit. But one thing that's cool about this is, my destructor is defaulted. I don't have to manually implement a destructor. I just hand it to the type, and it'll do the right thing. Here's how I implemented the type. It's just a struct with a call operator that takes the pointer type, and it calls the function. There's a extern C here to pull in the to declare that function exists, and you see the forward declaration of the type from the Rust side. I like to use a Rust namespace here just to make it clear that type is coming from Rust, but you can do what you want here. It doesn't really know anything other than it's a raw pointer to some type. The implementation at this point is really simple. All it is the constructor, and the constructor is initializing the unique pointer and calling that function. It's pretty straightforward. Actually, it's really pretty easy. It's really boring at this point. And we now have, with that, we now have a Rust or a C++ object that's move only that contains a Rust type, and you can create it and destroy it from C++. This is all stuff that code generators will do for you. The reason that I was in this situation is explained here. None of these code generators will generate None of the code generators will deal with library types. And when you're writing robotics code, you write a lot of matrix math, and eigen is the important library for doing that. And the code generator will not glue an eigentype to another library type. In Rust, there's this nalgebra library that is, I think, largely based on eigen. I largely didn't have to read the docs of nalgebra because I'm familiar with eigen, and everything that I just intuit works seems to just work over there. The types are very similar. The way they behave is very similar. So I wanted to write this function, this method, calculate transform, and I'm going to take a one-dimensional vector of doubles, and I'm going to return an isometry 3D, which is a 4x4 matrix underneath. And conveniently, we'll see later, both the eigentype and the one on the Rust side, internally, they're both column major by default. And I'm going to use that. That's going to be helpful. There's a little bit of weird syntax. If you're not familiar with Rust, on the Rust side of this function declaration, the @self is just the way to say that this is a method on the joint type so that I can use the dot operator to call, like, joint dot calculate transform. That's the like method call. It's similar to like a this, but it's explicit in Rust. The second one is a slice. So I got to explain a slice a little bit. A slice is a fat pointer. In Rust, to pass a dynamic size thing into a function, you need, similar in C, you need a pointer to the beginning and you need the size. And in Rust, we have a syntax for that, and it's just a slice. It's a reference to some block of memory. We can take them as parameters, but we can't return them for maybe obvious reasons. And then we're just going to return this isometry 3. To do this, we need a feature that I don't think is very well documented. If you've written a lot of C code, this might make intuitive sense to you, but when you're writing unsafe Rust code, there's a book that you need to read. It's the Nomicon, and it documents how unsafe Rust works. And it talks about the various types in the C interface. And one thing that you realize in there is that the memory representation of fixed size arrays, just like in C, if you put a fixed size array in a function parameter, it's just a pointer. The size of the fixed size array is a compiler construct. If you're going to do that over a link interface, right, you can't do it through a return type. You can't put a fixed size array through a return to the return. But what you can do is put a fixed size array inside of a struct, and then it has a size, and you can return that struct. Rust has a way of saying this struct has a C memory layout. You say repr C in this case. And then on the C++ side or the C side, I can look inside the struct. It's not going to do anything weird with the memory layout. And then secondly, we have C primitive types that let us use the platform types. So in this case, I'm going to use a double because on the C++ side, I'm going to use a double value because, right, I'm constructing that eigen matrix which has doubles. And I need 16 of them, right? It's 4x4 matrix. So here's the most complicated Rust we're going to look at. It's not as bad as it may appear. This is a C function that takes 3 parameters and it returns that matrix struct, the 16 elements. The first thing we have to do is unsafe. We have to take that raw pointer to joint that we got out of the unique pointer, or that comes from the unique pointer. We have to convert it into a reference or a borrow because we're going to dereference this thing. And that's because the compiler can't see through to the call site. We're going to write the call site, so we know it's always going to be valid. We're going to control its lifetime with the unique pointer, but the compiler can't see it. So we have to, writing Rust code, or unsafe Rust is all about the programmer checking things that the compiler otherwise would check, because the compiler's not able to check it in this case. The second thing is constructing a slice. Remember I said it was a fat pointer? So in C, if you were to pass a variable size thing through, or a variable size block of contiguous memory through parameters, the way you would do it is a pointer and a size, like we did here. The guts of a slice in Rust is just a pointer and a size. So we can construct one this way. This is also unsafe because in Rust, the slices are all guaranteed at compile time, and if you get a slice through a parameter, it wants to look at all the call sites and make sure that you never index past the end of it at compile time without runtime checks. The last thing here, we're just going to call the Rust function that I showed you the declaration for to get our transform. Then we're going to construct this structure, the matrix 4D. And these are like largely just a series of essentially typecasts to convince the Rust type system that the guts of this memory can be passed as a 16-element array. If you look at the memory inside of it, that's what it is. But we need a bunch of these little functions to do that. So on the culling side, on C++ side, in our implementation file, I put the CPP up there so you can tell that this is the source file and not the header. I have to declare the struct again because I'm going to look inside of it. There's a little bit of keeping these pairs matched up. This is some of the fiddly bits of doing manual interop, is you have to make sure that both sides are the same. You can get yourself surprising errors if you don't do that. And then we have to have the function declaration from the extern C to say we're going to call this thing. And then here is the implementation of calling it, right? We take the vector from eigen, right? It's similar to a stud vector if you haven't seen eigen before. XD is similar to stud vector, and it has, you can call get to get that start pointer, and then, or data get the start pointer, and then size to get the size of it. And then the robot joint.get, right? Remember, the first argument is the raw pointer to our Rust type that we want to be able to call a method on, and we're storing it inside the unique pointer. So we do that there. And then the last 3 bits, if you're unfamiliar with eigen, probably the most confusing bit of this is that the dot matrix function gives you a reference to the internal state of it, and then that expression on the end casts it into the right size to be able to do that assignment. And we're going to return the transform. And now we've glued the two together. That is the basis of having first-class types. Some of you might ask, like, what is the performance penalty of doing this? You saw that I was essentially copying the data. In practice, I wasn't able to measure it. I tried measuring it, but the compiler's really good at optimizing copying 16 doubles. There's a chance that like the pipelining or whatever in the processor really just ate that up and it was fine. So that we're eventually going to go into code generation, but it's sometimes really important to understand how manual interop works, because you want to expose to the two safe sides where the solid ground that everybody's used to, the types that they want to use, right? You don't want to just program with standard library types. You want to program with your domain-specific types. And in robotics, these are really important to us. So that's that. To summarize, doing manual interop, you create unsafe functions for creating and deleting objects. You can store an opaque Rust object in a unique pointer to end up creating a move-only type, right? We can't copy it because we don't, on the C++ side, we don't know anything about its size. And then we could implement, one of the things we could do, if you do need to be able to copy objects, you could implement C functions back over to the Rust side to give you copies of objects. We could implement clone on the Rust side to be able to copy objects. But if you don't have to, move-only types are great. Fixed size arrays are difficult to send out of return types, but you can wrap them in structures. That's something that's worked well for me. And then you can use the method implementations, pairs of method implementations and unsafe Rust code to bridge first-class library types. So your users have the types that they expect. That's cool and all, but I firmly believe you haven't really written a library until your users can use it. And one of the key details of letting your users use your library is make it work with their build system. So that's the next thing we're going to do. We have to glue these two things together. We got to teach CMake how to build this thing so our users who use CMake can use our thing. Right? We don't go to our users and be like, all right, we got a multi-step thing to be able to build our package. You're gonna have to invoke cargo, and then you're gonna go hunt for the paths for this library, and then you gotta hand jam your linker to get them to glue together. No, we're not gonna do that. In my situation, this is where I was, right? I have a bunch of coworkers. People I was planning on publishing this as an open source thing. I can tell you why it didn't end up being that later, if you want. But there's a bunch of people who've written CMake, and I wanted to be part of the ecosystem. I wanted them to be able to use my thing without knowing that the guts inside of it was a Rust program or a Rust library. I wanted to give them that. Nice. I did all that work to get first-class types in C++ with that header file. I wanted to give them a first-class CMake library. And specifically, this is what I want my user to be able to do. There are many approaches to exposing a CMake library to users, but this is one that I think we're starting to standardize, or at least is relatively easy for people to consume libraries if you do this. If you make this work, right? They can etch content on your library, and then they can target link libraries against your target. I'm just using the word bridge here as a stand-in for the library, and bridge CPP is my C++ interface to the library. So from my C++ user's perspective, the library is called bridge. It happens to live in a directory called bridge CPP inside this repo. We got to talk about file layout. And this may seem odd or unrelated, but file layout is semantic in the Rust build system. Specifically, in Rust, there's a source directory. Inside the source directory, you put a lib.rs, and that's the entry point for your library. That results in almost no configuration to the build system to get Rust to work. The information is encoded in the standard file layout that all libraries use unless they want to tell the build system that they did something different. So in my example, I have a repo with both my safe Rust library and my C++ interface. In Rust, the base package size is called, or package type is called a crate. So I have a crates directory. And then my safe code is over there on the left. Uninteresting for this talk. My C++ interface is over here on the right. It has a cargo toml because that's how I specified this is a Rust crate. We'll see the details of it in a bit. I have a CMake list because this is also a CMake package. I have a CMake template file for the config module. We'll look at that in a bit, and you'll see why I have to do that. I have my header file. This is my C++ user interface. This is what my users who are going to write C++ against this will want to see or need to include against. And then in my source directory, I have the lib.cpp. I just use the same convention as Rust uses here for my source. And then lib.rs, that's where that unsafe code goes. Of course, we need tests. safe to assume that no code works until you test it. It's also practical because we're writing these pairs that we have to keep in pair in 2 separate files, and it's really important that we exercise those code paths in our infrastructure, in our builds, just to make sure, just to help ourselves not make mistakes. It's good to run this stuff through sanitizers and to verify that you didn't create anything unsound. So here's the root cargo. There's nothing all that interesting here other than I'm saying that I have 2 member crates in this cargo workspace and that I set a version for all of my packages and I'm using the 2021 edition of Rust. Nothing really that special. All right, now we get into the C++ interface, right? It's a Rust package because we got to build that unsafe code first before we can link to it. There's a few interesting things in here. I'm going to give a name to the library and set it to build as a static lib. Rust libraries do not normally build into an archive with object files underneath it that you can link against. You have to ask it to do that. Lastly, in Rust, if you have a dependency that can be referenced via a path, you can specify it that way. You can get dependencies, obviously, through crates. By specifying a version, it'll go out on the internet and get it. But you can also just specify it by a path. If you have another crate, and in our case, this bridge library is the safe Rust library. And it is just in the sibling directory there. So now we get into CMake. This is all kind of boilerplatey CMake stuff. If you've written a lot of CMake, we need to specify a minimum version because we're going to use some features that require that minimum version. We got to specify the name of our project and its version. I think it's helpful to copy the version here from the TOML, cargo TOML, so that we all have the same version for our package. It'd be great if this could be automated, but I haven't figured out how yet. We have to find package on eigen. Remember, we have eigen in our public interface. And this is going to be important later, but it's important to specify it here so that we can build the C++ code. We'll specify it later for our dependencies also. Then we got to fetch content again. So I didn't teach CMake how to build Rust code, but somebody did, and they did a really good job of it, and it's really easy to use. There's this corrosion thing that you can fetch content and then use to build your Rust crate from CMake. And here's how you do it. It's just a CMake module. You have to pass a path to the cargo manifest. In this case, it's in the same directory, so it's just a file name. And then the crates that you want it to build. You can specify it building a bunch of different crates, but in my case, I only have one that I care about exposing. And then it's going to set up CMake targets I can link against for that static library. Here's basic CMake for creating a library and linking to a few things, right? We have to make our library. In my case, I'm going to build it as a static library. There's choices here, right? I need to specify my include directories, right? And I need to do it in a way to where my install works. It's really important. The most important part of this CMake is getting the install target of the CMake to work so that our users can fetch content against it and it'll work for them. And they don't have to know about our transitive dependencies or where our include paths are. This needs to come through CMake for them. We have to link against eigen as part of our public interface. We're linking against the Rust library as part of our private interface here. This bridge unsafe. Remember, that was the name I gave my Rust library in the cargo file. And then we have to specify a couple more things here. Position independent code is really useful in this case for our users. I'm not showing it on any slides here, but in the thing I wrote, I used a bunch of C++20 features, so I have to specify it there in my header files. Then we got to use a couple of these helper modules that come from CMake itself to write our install. We have to install our target. We have to tell it about the runtime, library, and archive destination. We have to name and export for it. We have to tell it we have these two targets. We have to tell it both the bridge target, which is the C++ interface our user is going to use, and bridge unsafe, which is the target it links against. Then we call the install on it to install the project. Then we have to generate the config module. This is the thing that makes find package work. So remember I said we got fetch content to work. We also got find package to work. So if our user has a more traditional CMake approach where they're going to build our library and install it, and then they want to find package against it, I also want that to work. So I need to specify a config module for that to work. And lastly, I need to install my header files, copy it to the correct destinations. Here is that template file. The template file is here because we have a transitive dependency on eigen. That's really why it's here. You wouldn't need this if you didn't need to add a find dependency on eigen in this file for our users. But by specifying this, when our users configure a dependency on us, if they don't have eigen, it'll fail early for them. We don't force our users to read our README and also include eigen. We make them, we specify it through CMake. So now with that, our users can interact with our library we built in a first-class way. Like a lot of what I think doing Interop well is about tidying up all the little details so that we don't expose the details of how we implemented it to our users. So our users get a first-class experience in the way that they're used to consuming CMake libraries. Or a better than normal experience in consuming CMake libraries. Writing install targets for CMake that work is hard, but it's very doable. The documentation is great. CMake isn't as hard as people make it out to be. It is very easy to do wrong, though. And it's important that you test your install. If you're interested in how to test an install of a CMake library, you can come bug me afterwards. I have a good friend of mine has a great public example on how to do that. But lastly, we're going to talk about the next thing that I did with Interop, and that is I was writing some Rust, or a new Rust project for myself, and there was a library that a coworker wrote in the past in C++ that I wanted to use in my Rust project. So I need to be able to call C++ code from Rust. And how am I going to do that? Well, that project, we got to look at the details of that project. And we're going to kind of implement the fetch content workflow in reverse from the Rust side. That package in this example is a CMake project that has Conan dependencies, Conan transitive dependencies. And we're going to make a Rust project that has bindings into that and is first class in Rust too, so that our Rust users don't have to know about what's in the guts. So to do that, we need some dependencies. This is how you specify dependencies that can come in from crates.io. The most important one here is the code generator CXX. It's magical. It uses, so under the hood, it does a few things. It's using libclain to parse C++ header files and reflect over them and then generate safe interop code so that from the Rust side, we have safe interfaces. It can also generate unsafe ones. And then we have some build time dependencies. So at build time, I need to know about CXX build. That's the thing that uses libclain, is going to reflect and set up stuff I can link against. We're going to use anyhow. Anyhow is a really common, it's also by the same author as CXX, but it's a really common library to deal with errors in Rust, and error handling makes it more ergonomic. There's a library called get2 that will shell out to get and run git commands, right? We're going to fetch content against this, so we got to run git commands. Somebody, I think, from JFrog wrote this Conan 2 library that lets us consume Conan recipes and do something smart about it. And then there's a CMake one that same sort of thing. So we gotta work through using these dependencies. The Rust build pipeline is very Unixy. And what I mean by that is it's going to execute various programs and pipe the output of one into the other. And that's how it passes commands from various stages to another. And one of those stages is it'll run this Rust program that you can write. The name of it, the file or the script is build.rs, and you just put that in your root, and then it will build this first and invoke it as in an early stage of your Rust crate build. This is the escape hatch for doing anything non-standard, essentially. So remember I said it was Unixy, so we got to send stuff to standard out to pass commands to the next stage. And there's a bunch of these, and they're prefixed by like what part we're going to command. And so we're going to tell Cargo that if this script changes, Cargo is all about caching things, so if I don't tell it to do this, if this script changes the next time you build, I want you to rerun the script. Also my source directory. And the reason for my source directory in here is because my source directory is going to contain Rust code that this script is going to reflect over to generate code. So if I change something in my source directory, I want this script to run again to redo the code generation. How this script gets input is through environment variables that are placed in the environment before this program is invoked. And one of the important ones is the output directory. It's like the working directory in the target directory where we're building things. And I need this because I'm going to check out a Git repo in it and build a CMake project. This is how you check out something in Git. It's pretty straightforward, right? You need the URL to it, and you need a path for where you're going to put the thing. You test to see if it exists, like, did I check it out before? You get fancier here, and you could maybe check the hash of it and see if the remote hash changed. I didn't in this case. But this is the basics of getting your build to check out this Git repo. The next thing is Conan. So this Conan library will parse recipes and build the missing ones into the Conan, your Conan package install, and then parse it. One thing that's cool about Conan 2 is it has a JSON output, and this is all based on that. So you can invoke Conan and have it output JSON instead of standard out, like the normal like log stuff. And then from that, you can tool around it. And so that's what this is doing. It's shelling out and invoking Conan and then parsing the JSON. And from that, I need to know the include paths of all the transitive dependencies of my dependency that I'm going to build. I need the toolchain file because I got to pass that into the CMake for the dependency I have, data tamer, that is a CMake project that depends on Conan dependencies. Here I'm invoking CMake. It's pretty. The next thing here is just passing in that toolchain file to CMake, and then calling build, and from that I can get the installed information. Right, I need the library path of this thing so I can link against it, and I need the include paths so that I can have the code generator is going to use libclang to parse these and reflect over and generate me bindings. This is the bindings generator. This is the invocation of the reflection tool. It's going to read my Rust code because I'm going to put the instructions for the code generation in my Rust code. You express it in Rust. And then I have to tell it about the include directories it's going to use. I'm going to include my source directory. And it's because I did something kind of clever, or I think kind of clever. This code generator knows how to use template functions, but it doesn't know how to call special functions like constructors. I just wrote a template function that can call constructors, and I'm going to use that in my code generation. You have to specify a C++ standard. In this case, 17 is the newest. It'll give you the most features out of the code generator that the code generator used. And then you have to give it a name. This is just an intermediary product in the build pipeline. It doesn't really matter. It auto hooks it up and stuff. We have to link against that library, that CMake library, our dependency that we're building. And then lastly, we need to omit the instructions from the Conan instructions that will set up our links on the transitive dependencies of our dependency. You see, this is way more involved than just fetch content. But it's not that bad. It's all kind of just basic things, right? It's the steps that you would take if you were to look at the README for this package. It would walk you through doing this on the command line, right? You would check out the Git repo. It might not tell you how to do that, but we can assume you know how to do that because you found it on GitHub. You can check out the repo. It's going to tell you you need to have Conan installed to get the dependencies. You're going to invoke the Conan command, and then you're going to invoke CMake and pass the toolchain file that came from Conan, and then you're going to install you're going to build and install your CMake. And once you do that, then right you can link against it. So that's all we're doing here. It's just expressed in Rust. It's a little bit more verbose. You could write functions that do this if you had a bunch of different dependencies. So here's the header file that I wrote. All this does is call make unique. What is kind of clever about this is the Rust code generator knows how to call this free function. And the syntax is pretty nice to do that. I couldn't get it to call make unique directly, but I could get it to call this thing. And I don't really understand why, but this is something that I found from the author of CXX was advising somebody to use this technique to get at constructors. And here's a little example of using the code generator. So on the Rust side, we're going to write this little block of code in the top is the stuff that the code generator is going to parse our Rust code and find this block, and then it's going to expand into the interop. It's saying, I have some C++ code I want you to read over. I have 2 header files I want you to parse. Right? That datatamer.hpp is going to include recursively include a tree of header files, including all the way down through the transitive dependencies and stuff. There's a type. In this case, just specifying the type this way says I want it as an opaque type. I'm going to interact with it as an opaque type. And then there's a unique pointer, which matches the C++ unique pointer. And then I can call this construct unique function. In Rust, we don't have function overloading. So we need unique names for all of our functions. And there's another macro that says that when you build the matching pair, name the Rust function something else, so that I can use this function a bunch more times. Even though it's a template function, I need that. And then here's my little example of my main. I can construct my registry, which I'm then later going to use to invoke all sorts of functions on this thing. And with that, I was able to code gen all of the interfaces for this thing that I wanted to use, and then use the C++ library. And my Rust users, if I was building this into a library, I was building it into an application. But if I was building it into a library, I could re-export some of this stuff, and I could have Rust users that could use it, and it would just work as part of their builds. Like, they could pull it down from crates, and when they execute it, it would execute my build.rs, and it would check out the file and build the Conan dependencies. It would probably fail if they didn't have Conan installed. I'd have to tell them to do that. But just like anything, you have to have the tool chain programs installed, and in this case, Conan is a tool chain program. Going in the other direction, we have a similar situation, right? I made it first class from a CMake perspective, automate it, they still have to have a Rust toolchain installed for that to work, right? Because it's going to build on their machine. So, in conclusion, Rust and C++ can work together. It's simpler than you think. You sometimes have to try multiple things to get it to work. You have to be creative about your approach to it. You have to glue things together that sometimes aren't natural to put together, but it can be done. It's not that bad. And there's all sorts of helpful tools that exist that do most of the work for you. You don't have to. You're not starting from zero. Like there's a lot of people doing this, and they're building really helpful tools. They're out in the ecosystem, and they work together really well. Anyway, thank you. Questions?
Hey, thanks for the talk. We're going to use this right away, so this is an incredibly useful talk for us. I had a couple of comments. The first one is when you created your Rust functions that are exposed to C that take in C pointers.
Yeah.
I think those should be marked as unsafe because technically you can call them outside of their preconditions and have undefined behavior. That was like a little tidbit when we were figuring this out.
Yep.
Think about that.
Yep. I think that was just a mistake. I'm sorry. It was a good point. You caught that.
The second one is when you're using this methodology to where you create static libraries that are generated with Rust and you bring them into a larger application. A problem that we encountered with that is that if you do that multiple times, each one of those static libraries has the same like Rust runtime functions and things along those lines. And so you can potentially get into ODR violations. So one of the things that we've had to do with our like internal build system is generate like a single static library that brings in all the different Rust crates that we want to use and then use it like that. So
that's a really good point. I hadn't ended up in that situation because I wasn't bringing in a bunch of different ones. But yeah, that's a great point. Thanks for pointing that out.
Hi. Have you found any issues or solutions to exception handling between the boundary? Have you had to find ways to wrap exceptions or anything like that, or do you just have to go straight to error coding?
So CXX does some really cool stuff for that. CXX will actually, if you panic from the Rust side through call stack, will convert that into a C++ exception, and in the opposite direction will I think convert it into a Rust panic. In some cases, it'll just call terminate on the boundary, but in a lot of cases, it will glue that together. I've never manually built that functionality, but CXX has done that for me before.
All right, thank you.
Yeah, that was a good point.
Yeah, thank you. That was a really amazing talk. I want to try this now right away. So what you showed is basically how to solve like the technical side of generating the bindings, right? But there's another aspect to it in that as soon as I fall out of the unsafe block on the Rust side, I need to make sure that like I didn't violate like any of the invariants that the Rust borrow checker expects, right?
Yep.
And that to me, like at the moment, seems to be a bit of a blind spot because that's not something that's usually well covered in teaching materials for Rust, and it's also not something that these tools address, right?
Yeah, the tools. Well, CXX uses a bunch of static analysis with the Clang tooling to try to make so that the safe bindings that they generate don't have that problem. But that's a really important part about writing unsafe Rust code, and it's something that you'll pick up from reading the Nomicon. Is they talk about, you know how in C++ if the compiler can just like delete null checks on you, and there's all sorts of things the compiler can do because it has to assume that UB doesn't exist. And Rust is the same way. It has to assume that UB doesn't exist. And if you write UB, your program isn't going to just blow up in the unsafe block. You can, if you invalidate or invariant inside the unsafe block, you can make your safe code unsafe.
Yeah. So, like, if somebody now wanted to try this with a non-trivial library, like, do you have any advice how to tackle this problem other than read the Nomicon half a dozen times?
I mean, I think that's probably the best we have. Use CXX. Try to just use CXX through its safe interfaces. It does put some restrictions on what you can interop because they were really, they really specifically had the goal of only using stuff from C++ that they could safely represent in Rust without violating any invariance. One side effect of that is there's like no nice way to send a shared pointer across the interface. And the reason is because it's assumed that there might be another shared pointer copy somewhere out in the C++ code, and that could make all of your Rust code violate an invariant. So that's an example.
Thank you very much.
Yeah.
Thanks a lot. I'm curious, like when you were surveying for this and when you're trying to figure all this out yourself, because I've done some sorts of interop things before, and it's always like a little bit confusing on like, have we standardized on a way to set up our projects, on a way to do all this stuff? How settled do you think like the community is in doing one thing right now?
I can't speak for the wider community, but I can say how I got here. I just went looking for working examples. From people that I knew did good work.
Right.
And specifically, I just went to the author of CXX and went and found other projects he worked on. And then I was able to read them and figure out like, oh, this is how you structure these things, and here's how the relationships work. I had a former coworker also do this, and we ended up in similar places, and I got to learn a lot from what he did that also found its way in here.
And like the various examples you've been seeing are generally the same kind of solution space?
Yeah, it feels kind of feels like it's kind of standardizing on an approach, but it is kind of the Wild West in a lot of ways too. There's a lot more stuff to explore here. There's a lot more stuff to figure out. It is new.
All right, thank you.
Yeah, thank you. Also to note that this content largely came from 4 blog posts I wrote earlier in the year. I'll put links to that in the Discord if you would like a longer form of this full of comments and stuff that you can copy and paste. And there's a lot of links to the various resources there where I learned this stuff. But thank you.